Let's take a look at a couple of your clicker questions. Which of the following compounds will produce a basic solution when dissolved in water? First step, dissociate. Got Na plus nitrate ion. Let's examine the anion. The anion nitrate is the conjugate base of a strong acid, HNO3. We know that the anions of strong acids, they are neutral. Okay? Sodium cation, we've talked about it extensively. It is the cation in the acid-base reaction from sodium hydroxide. It's a strong base, and so it is neutral. HF, when it's dissolved in water, is going to ionize a little bit. It's a weak acid to form H plus and fluoride ion. The addition of H plus will cause the pH to decrease below 7, not a great deal below 7. It is a weak acid, and we're looking for the most basic solution. This is also going to dissociate NH4 plus. We get Cl minus. We look at the chloride ion. It is the conjugate base of the strong acid HCl, so it is neutral. We look at the cation. It is the conjugate acid of NH3, which is a weak base, and so this is going to be weakly acidic. This will have a pH that's just a little bit less than 7. Sodium carbonate will dissociate completely into 2 sodium cations plus carbonate anion, and it's got a 2 minus charge. We'll examine the sodium cation first. You guys, we've already talked about it. It's a neutral cation. The carbonate, on the other hand, is the conjugate base of, if we take a look at it, the conjugate base, I'm just going to add a proton to it, see what it's the conjugate base of, HCO3 minus 1. We can consider in this context that the carbonate ion is the conjugate base of a weak acid, therefore it is a weak base, and it's going to cause the solution to become basic. So the reaction is CO3 2 minus plus H2O in equilibrium. It's going to pick up a proton off of water in hydrolysis, make a little bit of the conjugate weak acid plus hydroxide ion. In reality, bicarbonate itself is also typically basic as well. It's going to pick up another proton off of water in an equilibrium reaction. It's behaving as a weak base. It's going to make the weak acid carbonic acid, which you get a dose of every time you drink a carbonated beverage, and it's putting hydroxide ion. So your answer is D. This will be the most basic solution. Sodium chloride, on the other hand, is a neutral salt. You've got a neutral cation, chloride, and a neutral anion. Sorry, neutral cation, sodium cation, neutral anion, chloride ion. When NH4 is dissolved in water, the solution will be, hopefully by now, you have worked this out. This is NH4Cl. It's going to dissociate completely into NH4 plus Cl minus. The chloride ion is the conjugate base of HCl. It is neutral, and NH4 plus is the conjugate acid of NH3. NH3, of course, is a weak base, and this cation then is weakly acidic. So this will be an acidic solution. Which of the following reactions is responsible for the resulting pH of sodium acetate? So take a look. Now, be careful with this. We're looking for the reaction that's responsible for the pH. Now, Sodium acetate is in water going to dissociate completely. This is a completely soluble salt, but this dissociation is not what is changing the pH of the solution. However, if you take the acetate, which is the conjugate base of acetic acid, and you put it in water, this is the chemical reaction which we call hydrolysis. It's going to split a proton off of water, make a little bit of the conjugate weak acid and a little bit of hydroxide here, which is going to make your pH a little bit greater than 7. I don't know. It depends on what the concentration of the sodium acetate is. Okay, which of the following substances will give an aqueous solution a pH of pH closest to 7? Well, we're looking for a neutral salt, and we'll just describe each one of these. This is going to be K plus NO3 minus, this is the conjugate acid, or this cation comes from potassium hydroxide, so it is neutral. Nitrate is the conjugate base of HNO3, which is a strong acid, so it is neutral. So this will have a pH equal to or very close to 7. This is a non-metal oxide, carbon dioxide, which is actually going to combine with water in an equilibrium reaction to form carbonic acid ultimately, which is the acid that you have a little bit of tingle in your mouth when you drink your carbonated beverage. This is going to be an acidic salt, NH4 plus iodide. Iodide ion is the conjugate base of hydrogen iodide. It's neutral. This is an acidic cation. We've talked about it before. This is NH3. Combine it with water in an equilibrium reaction, get NH4 plus some hydroxide ion. So that's going to be basic. And then here we have methylamine, which is very similar to ammonia. It is also going to combine with water and make methyl ammonium cation and hydroxide ion. So this would be basic. Salt pH 1. Calculate the hydroxide and pH for a 0.1 molar solution of sodium cyanide. So first of all, let's ask the question, is this an acidic, basic, or neutral salt? Well, let's do what we're supposed to do. Let's dissociate it. So that's sodium cyanide. We're going to dissociate it. We get some sodium cation and some cyanide anion. Let's just go ahead and eliminate the sodium cation. We've just talked about it ad infinitum. You know it's neutral. And then cyanide ion. Well, cyanide ion, if I look at this anion and I ask myself, what is it the conjugate base of? It's the conjugate base of hydrocyanic acid, which is a weak acid. So this is going to be a basic anion because it's the conjugate base, it's the anion of a weak acid. And we all know now, by now, hopefully, that the conjugate base of a weak acid is a weak base. The reaction is going to be cyanide plus H2O in equilibrium. We're going to make a little bit of hydrocyanic acid, this stuff right here, and a little bit of hydroxide. So we know we're going to have a basic solution. A couple of things that we need to sort out first. So when this dissociated, if this was a 0.10 molar solution of sodium cyanide, then the concentration of both sodium cation and cyanide is also 0.10 molar. All right, so that means we've got a 0.10 molar solution to start. That's our initial concentration. We don't care about water. we don't have any hydrocyanic acid or hydroxide initially. Our change is going to be minus X. We don't care about water. It's a constant 55.5 molar at 25 Celsius. We're going to add a little bit of this, add the same amount of this, and at equilibrium, we'll have the initial 0.10 minus X, and then down here we have X, we have X. Now let's take a look at the equilibrium constant expression. This is a weak base, so we can't use the Ka for the conjugate base of hydrocyanic acid. We need the Kb. And if you remember, Ka, that is for the hydrocyanic acid, this stuff right here, times Kb, and the Kb is for its conjugate base, and that equals Kw. So we're going to go ahead and we need to solve for the Kb. We have the Ka, we have Kw at 25 degrees Celsius. So the Kb will simply be equal to Kw divided by the Ka that's given for the hydrocyanic acid. So that's going to be 1 times 10 to the minus 14, keep in mind that's only at 25 degrees Celsius, divided by 4.9 times 10 to the minus 10. I reach out, I grab my handy-dandy calculator, which is not here. When I plug this into my calculator, I come out with a Kb that's equal to 2.0 times 10 to the minus 5. All right, now I'm ready to do some math. So my equilibrium constant expression, which I urge you to always do first, is going to be Kb is equal to HCN times hydroxide ion divided by the concentration of the cyanide anion, which is your weak base. Once I have that, I'm going to go ahead and plug the values in from the equilibrium constant, from the ICE table, but I need to take a look at this X and compare it to my Kb. Now, my Kb is equal to 2.0 times 10 to the minus 5. All right, and my concentration here is 1 times 10 to the minus 1 if I put it in scientific notation. And that is 4 orders of magnitude difference, which should make it very safe for me to ignore X relative to the starting concentration. But just to be sure, once we're done with the problem, we're going to go ahead and we're going to calculate the percent ionization. So here we go. 2.0 times 10 to the minus 5 is equal to X times X, which is X squared divided by 0.10. Now, if I included that X down there, I'd wind up with a quadratic equation and have to use the quadratic formula to solve. I'm going to go ahead and multiply both sides by the concentration of cyanide ion. I'll do the same thing right here. I'm going to distribute that, I'm just going to multiply right there. So that's point times 0.1, and that gives me 2.0 times 10 to the minus 6. Well, I should have guessed that. So that's 2.0 times 10 to the minus 6 is equal to X squared. How do we get rid of the square? You know this. We're going to take the square root of both sides, which gives us X. And in this case, X is equal to the hydroxide ion concentration. So I'm just going to take the square root, and that gives me 1.43 times 10 to the minus 3 molar. 1.43 times 10 to the minus 3 molar in hydroxide ion. I'm going to go ahead and get the POH by taking the negative log of the hydroxide ion concentration, which is 1.43 times 10 to the minus 3. Can you guess, will the POH be greater than 3 or less than 3? And ask yourself this question, or maybe even type it on your calculator. If you took the negative log of 1 times 10 to the minus 3, what would you get? You would get 3. But as the hydroxide ion concentration goes up, just like the pH, the POH goes down. So when I take the negative log, I get 2.85. 2.85. And to get the pH, I use this equation. pH plus POH is equal to pKW. And we know at 25 degrees Celsius, pKW is 14. We now know that the POH is 2.85. And all we have to do to get the pH is subtract 2.85 from 14. So the pH will be equal to 14 minus 2.85. And so that's 14 minus that. And I get 11.15. 11.15. Okay, that was a pretty good problem. To sum it, we need to make sure that when we're giving, and this is going to happen a lot, you're given the Ka for a weak acid, but you're being asked for the pH of the salt of its conjugate weak base. We could go the other way. Let's see. We could go the other way and calculate the pH for the conjugate weak acid of a weak base, like ammonia. All right, so here we go. So salt procedure, write the equilibrium established by the weak electrolyte, trying to get back to the molecular form. That's what the anions and cations of weak electrolytes do. They react with water to try and get back to their more stable molecular forms. That's why they react with water. Identify or calculate the K value for the reaction. If it's a weak acid calculation, you need a Ka. If it's a weak base calculation, you need a Kb. Use an ICE table for your calculation and solve for whatever it's asking for, either hydrogen ion or hydroxide ion. Okay, so salt question 2, calculate the pH of a 0.05 molar solution of ammonium chloride, and they give the Kb. So this is the same idea, but we're going in the opposite direction. First thing you do, dissociate the salt. The salt is NH4Cl. The concentration of the salt is 0.05 molar. It's a strong electrolyte. It dissociates completely into NH4 plus, Cl minus. Just so you know, the Cl minus is the conjugate base of HCl. It's a neutral anion. But the NH4 is the conjugate acid of NH3. NH3 is a weak base, so NH4 is a weak acid, and we're going to treat it as a weak acid. Since it was a 0.05 molar solution of NH4Cl, it's going to be a 0.05 molar of NH4 plus. So here we go. So NH4 plus in equilibrium. We don't really need to include water because it makes chemical sense. It is in water. That's absolutely true. But it makes chemical sense if we exclude water in this particular case. We get H plus plus NH3. And of course, it is all happening in water. This is 0.05 molar We don't have any ammonia or hydrogen ion to start with. This is our ice table. And this is going to be minus x plus x plus x, and 0.05 minus x, x, and x. Now, they give us the Kb for ammonia, NH3, but we don't need that. We need the Ka for its conjugate weak acid. So, once again, Ka, this is for NH4 plus, times Kb, and that Kb is for ammonia, the conjugate weak base, is equal to Kw. We can solve for the Ka. Ka is equal to Kw divided by the Kb. Kw at 25 degrees Celsius is 1 times 10 to the minus 14, and the Kb is 1.8 times 10 to the minus 5. When I solve that, I get the Ka for NH4 plus, sorry about the handwriting, guys, is 5.6 times 10 to the minus 10. I'm ready to solve. First of all, let's go ahead, make sure that we're okay ignoring that x. And I have to say, on any test, I'm going to make sure you can ignore that x. I'm not going to ask you to do the quadratic formula for a quadratic equation on an exam. It's not an algebra class, even though we use algebra constantly in it. Okay, so 10 to the minus 10, this is 5 times 10 to the minus 2, so that's 8 orders of magnitude. We can ignore that x. So that gives us 5 points, let's go ahead and do the equilibrium constant expression, which is Ka is equal to H plus times NH3 divided by the NH4 plus concentration. All right, I'm ready to solve. So that's going to be 5.6 times 10 to the minus 10 is equal to x squared divided by 0.050 molar. I'm going to multiply both sides by 0.05. And it cancels over here. Let's see what we get. So I've got 5.6 times 10 to the minus 10 times 0.05. And that gives me 2.8 times 10 to the minus 11. So now I have x squared is equal to 2.8 times 10 to the minus 11. I'm going to go ahead, take the square root, and that gives me x, which is equal to my hydroxide ion concentrate. I'm going to go ahead and solve for x, which gives me my hydrogen ion concentration, and that gives me 5.29 times 10 to the minus 6 molar. 5.29 times 10 to the minus 6 molar. That is in hydrogen ion. I can get the pH directly by taking the negative log of the hydrogen ion concentration, 5.29 times 10 to the minus 6. I would ask you again, is this going to be greater than 6 or less than 6? You know, if you took the negative log of 1 times 10 to the minus 6, you would get 6. But because the hydrogen ion concentration is higher than that, the pH is lower than 6. So you're going to get a number less than 6. So there we go. And we get 5.29 5.28. You get a pH of 5.28. It is indeed acidic. I will say that when you know you're doing a weak acid problem, typically it just looks like this, HA, that's your generic monoprotic weak acid, equals H plus plus the anion. If you know your numbers and you know what you're doing, you can actually get the hydrogen ion concentration, which is equal to X, which is going to be the square root of the Ka for that weak acid times whatever the concentration of that weak acid is. So that is a shortcut that will get you there a lot faster, but you really do have to know what you're doing. Oh, let's go ahead and calculate the percent ionization just to be sure. We've got 5.9 times 5.29 times 10 to the minus 6 divided by our starting concentration, 0.05, times 100. So there we go, 5.29 times 10 to the minus 6 divided by 0.05 times 100, and I get, looks like 0.011%. So my percent ionization is very small at 0.011%. Okay. This one's really easy. I'll go ahead and do it. All you have to do is recognize that this salt is completely neutral. Dissociate it completely. Look at the anion, which is the conjugate base, the anion of HCl. You know that it's neutral. Sodium cation is the cation for sodium hydroxide, which is a strong base. So you know that the cation is neutral. The pH of this guy is 7.